Hello, and welcome to AMAT362, Probability for Statistics at UAlbany. So last lecture, we introduced some of the foundations of set theory, specifically some of the notation of what does it mean to be an element of a set, what's the complement of a set, what is the complement of a union, which led us to, of course, De Morgan's laws. This lecture, we're going to see why we needed that set theory to get to one of the first foundational definitions for probability theory. And this is embodied by something called Kolmogorov's axioms. As I alluded to in our first lecture, there are competing definitions or perspectives on probability. One's sort of frequentist and others Bayesian. But in some sense, Kolmogorov's axioms work in both. However, the interpretation of the quantities involved differ when we think about frequentism versus Bayesian. I'm going to then focus on the sort of setting where there are a finite number of outcomes and looking at uniform probability, which leads us to just the problem of combinatorics, which is another way of talking about counting. So this is really combinatorics. All right, so let's get down to it. The motivating picture, which I drew last time, is that probability studies experiments which have random outcomes. And I sort of tried to draw this with this idea that there are several arrows, meaning there are several possible places that you could land in this cloud of possibilities. This is the sort of set of all possible outcomes. Omega. And that one way of thinking about what a random variable is, which we'll denote sometimes with the letter capital X, is it's a thing which assigns to an experiment an outcome, but it does so in an unpredictable way. This sort of cloud of possibilities is sort of more formally called the sample space associated to our experiment. All right. Now, what do we need to study omega for? Because in some sense, the probability of an event is in some sense asking, if I see an experiment, if I do something and it lands in this set of possible outcomes, does it always land here, or does it just land here 99% of the time? What that really means is we need to be able to identify the probability of an outcome. But we'll already see here there's going to be two important settings. So just as foreshadowing, so in discrete probability, this is characterized by this setting where omega is a finite set, or at least a countable set, which means that it can be things like, a set of n elements, like the alphabet. Examples, omega could be heads or tails when I flip a coin, or it could be, the letters in an alphabet, B, C, D, all the way up through Z. Or even we could have settings where any natural number is possible. So, this looks like the set of numbers of the form 0, 1, 2, on through infinity. This should be contrasted with continuous probability. This is the setting where omega is like the real line, meaning we've got a whole continuum of possibilities. We had an example of this where we looked at income. One of the problems with continuous probability is that you can sometimes specify an outcome and there's a 0% chance of that thing happening. So for example, if I asked, what's the probability that I pick someone off the street and they make $55,672 and 0.0317 some odd cents. I get to specify something arbitrarily precisely. And in that setting, the probability of actually finding someone who makes that exact dollar and cent amount becomes 0. So this is why you need to be very careful about what we actually assign probabilities to. And this gets at what's known as the definition of the event space. So I'll just say the problem is, I look at, what's the probability of someone making $55,272 and 0.3165432159 repeating cents is equal to 0. This is reflected in another problem. So I can call this problems. So imagine I throw a dart at a dartboard, where I've got, a bullseye here, and then I've got if the outcome is that the dart lands at exactly some location, bing, like this. So that's our dart. Because there are actually uncountably many locations for the dart to land, if I specify a location exactly, the probability of hitting that exact location, zooming in onto the level of atoms, becomes 0. So this all illustrates that we need to be precise about what we mean by events. So let me get into that a little bit here. All right, so let's talk about the definition of an event. So here's definition. So probability assigns chances to events. We're going to think of an event as a subset of the set of possible outcomes. So when we talk about the set of subsets, this leads naturally to something called the power set. Definition, the set of all subsets is sometimes written P omega. And these are the elements of this set are subsets A, such that A is a subset of omega. So here's a quick question. If the size of omega is equal to, I don't know, 5, then how big is the power set of omega? Well, there's a sort of nice trick here. The answer is, in this case, the size of omega is 32, which happens to be 2 to the 5th. And in general, if the size of omega is n, then this implies that the size of the power set of omega is 2 to the n. So let's try to see why. So this involves sort of an encoding trick. So you want to think of it as each subset A, which is a subset of omega, is encoded by a vector which essentially just indicates whether or not that element is in the set or not. Each xi is equal to 1 if xi is in A, and it's 0 if xi is not in A. And so now the question reduces to how many possible vectors of zeros and ones are there? Well, notice this is again actually expressing our set of possible subsets as sort of a product of zeros and ones. So we end up getting that power set of omega just essentially asks the question, yes or no for every element. Is it in the set or not? So that's 2 possibilities for the first element, and then 2 possibilities for the second element and third element, which ends up equaling 2 to the 5th. All right, so that's nice. And notice that in particular, the empty set, so all right, nota bene, the empty set, this corresponds to the vector of zeros. So this means that no element is in the empty set. All right, so that's a good sort of combinatorial exercise that you should have a handle on. We can go through some other examples of this later, but let's talk about what do the set of events need to satisfy. So let's go ahead and make another observation. So here's a fact. If omega is finite, so this is the case for discrete probability, then every subset of omega is an event. But in continuous probability, that's not always the case. So let me just write down what are some requirements on what an event needs to satisfy. So here's a definition. Let me write it this way. So this is the axioms for the set events. I'm going to write this events as a curly E, which kind of looks like a backwards 3. So the first one is that omega has to be an event. So this is sort of corresponding to the thing that anything occurs. So that's an event. Number 2 says that if A is an event, then a complement is an event. And then 3, and this is sort of the harder one to understand and won't be as necessary earlier in the course, but later on will be more important, which is that if A1, A2, AN is a countable collection of events, then A1 union A2, so on and so forth, which I'll write using the compressed notation. This is the union from k equals 1 to infinity of AK. This has to be an event. So essentially these 3 axioms say that I need the whole subset of omega to be an event. That just corresponds to the fact that anything can happen as an event. If A is an event, then it not occurring is also a possibility. That's an event. And then if I have a countable collection, think finite collection of events, then the union of those events is also an event. Let me sort of specialize and show you. Well, let's first get at what this all means in terms of defining what is a probability. So here's the definition, and this gets at this is really Kolmogorov's definition for what a probability is. Now, we'll drop the sort of fancier term, but let me include it for now. So this is the answer to the question. And it's this. So a probability is really a probability measure. It's a way of measuring the probability of an event. So a probability measure is a function P from the space of all possible events into the unit interval 0 to 1. So you want to think of this as the thing that takes an event, A, and it maps it to P of A, which is the probability that A occurs. And of course, there are some common sense notions that we need to encode into this. These are, one, that, of course, probabilities are non-negative. And that's kind of just baked into me writing this. So in particular, probabilities can never be negative, and they can never be greater than 1. So 2 is that, so where we require these further things. Moreover, that the probability of anything happening is 1. Something must happen. That's sort of an intuitive, more formal way of expressing that intuitive fact, which in particular implies that the probability of nothing happening is equal to 0. 3 is we need this following way of translating unions into sums. And here I'm going to add an extra assumption. So if A1 through A2 through A3, AN is a countable collection of disjoint events. So that means that AI intersect AJ is equal to the empty set for I not equal to J. So then the probability of this union, k equals 1 to infinity, of AK equals the sum. So 3 is sort of a fancy version of generalizing a simpler statement. So I'll write it here. So here's the easy version of 3. So that says that if I have two events, A and B, and if they're disjoint, which means mutually exclusive, disjoint, i.e. mutually exclusive, then P of A union B is equal to the probability of A plus the probability of B. So this is so useful. I'll go ahead and box it up. Now, how should you think of what this probability is? So I want you to think of the following. So let me just go ahead and maybe use a little bit of intuition here. So here's our intuition. So you can think of probability as the function which measures the percent area. So in particular, if I've got a box like this, and it has some area which I'll assume is 1. So let's imagine that the total area is 1. And imagine I've got two subsets. One that looks like this, A, and I've got another subset, B. Then I can think of the probability of A as being the area of A. And in general, maybe if I just called this, instead of saying the total area is 1, let me say that the total area is something like S, then I could think of this as the area of A divided by the area of S. Actually, let me go ahead and call this actually omega. So if I think this is omega, then this is really the area of omega. Now notice that here, if I wanted to figure out the area of the union, A union B, then it makes sense to just take the sum of the areas. But if I had another shape, I don't know, C, then I would have a situation where the probability of, or the area of A union C is actually bounded from above by the area of A plus the area of C. because I'm double counting this intersection when I look at the sum of these areas. I'm double counting the sum of those regions. So this really requires this assumption here. All right, so that's sort of fast forwarding a little bit to the continuous realm, but I want to try to stay simpler and discrete because the goal today is to get into combinatorics, which are sort of ways of determining probabilities when we have a finite set of possibilities. So there's another example that kind of parallels this one here with the area. So let me go ahead and do this. So it's an example. So the uniform probability measure on of, let me say this, on a finite omega is defined as follows. So I just take it's going to be equal to the size of A divided by the size of omega. So this is the setting where every outcome is equally likely. So that's another way of interpreting this, is every outcome is equally likely. Then the way to determine the probability of an event is just count how many outcomes are in that event and then divide it by the set of all possible outcomes. You know, think about it. When I looked at the deck of cards, and I said, oh, what's the probability that my first card that I draw is a king? Well, there are 52 possibilities, and there are 4 ways of getting a king corresponding to 4 suits. Then I just took 4 divided by 52. Let me just go ahead and write that down real quick. So example, draw a card, compute what's the probability of a king. And again, when I'm drawing a card, we're essentially using the assumption that this draw is happening uniformly at random, meaning every face value is sort of equally likely, or every card is equally likely. So what we have to just do is we take the number of kings divided by the number of cards. And so that's 4 over 52. All right, so those are obviously really simple examples where it's just sort of easy to directly count how many cards or how many ways there are of obtaining an event. It means counting the number of outcomes. But in general, we need to be a little more, we need sort of a fancier set of tools. So let me introduce some general principles here. So this now gets us into the following lesson. So computing uniform probabilities requires lots of tricks for counting, i.e., you can think of this as combinatorics. We're going to use all sorts of different ways of sort of thinking about how to compute possibilities. But one of those ways is going to be using things like tree diagrams, where we can try to measure through a garden of forking paths all the possible ways of obtaining an event. So let's go ahead and just sort of put down one of the very first ways of counting. And this is something called the multiplication rule. So here's the multiplication rule. So lesson 1. And this lesson essentially says that, suppose our experiment can be broken down into k parts, k steps, where each step I has ni possible outcomes. Then the total number of outcomes we can think of this as the size of our sample space, omega, is given by a product n1 times n2 times nk. Let me separate this. I guess I'll go ahead and write it here. So let's do some examples here. So we go do, oops. So example 1. Let's suppose I flip a coin 3 times. Well, here I've got an experiment which is naturally separated into basically those 3 parts. Meaning I flip a coin once, there's 2 possibilities there. And then I flip it again, there's another 2 possibilities. Flip it again, there's another 2 possibilities. So that's 2 to the 3rd, which is 8. Let's look at another one. So we imagine we have, Yahtzee. So remember, in Yahtzee, one of the things we do is we want to roll a collection of 5 die, which equivalently we can think of as rolling a single die 5 times. So here we have in Yahtzee, we roll 5, and I'm going to say that these 5 die are distinguishable. Now, the question of whether or not these die are indistinguishable or not is going to be a subtle one, which we'll consider later. But we can think of this equivalently as rolling a single die 5 times. And so in this setting, again, we've got omega equals 6 possible outcomes, and we need to do this 5 times, which is 6 to the 5th. Gone ahead and actually computed that out for you. It's 7,776. It's sort of an interesting number. It seems pretty lucky to me. So here's another example. So imagine I am ordering off of a prefix menu, and I just want to consider the set of possible meals that I could construct. And so the way that this usually goes is first you imagine you've got, super salad. So that means we have sort of two choices already here. So let me write this as here. So that's our, our first course. Our second course is, pasta, fish, or steak. And then we have two possible desserts. So we've got a, apple pie, or a brownie. And so if you want to ask what are the total possible number of meals, well, we start off with these two possibilities, and then emanating from each of those is then, did you choose pasta, fish, or steak? And then further, we have the separation into brownie versus pie. And so you can think of ordering from this menu as a walk. Here you're starting here before you've ordered. And then do you choose soup, steak, and apple pie? Or do you choose soup, pasta, and brownie? And then counting the number of ways of walking from that root node is just computed actually by counting the number of leaf nodes being these guys down here at the very end, which, amounts to just multiplying this number here. So now we've got number of leaf nodes equals 2 times 3 times 2. So that ends up being 4 times 3 is 12. And we can just check for ourselves. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this right here is called a decision tree. And it's a really useful thing to study when we're doing some of these combinatorial problems. So I want to consider another situation, which is maybe a little more esoteric, pun somewhat intended here. So this will be our fourth example. These go to tarot cards. And actually, I'm wearing my tarot card t-shirt, which has a big 22 in the center. The reason why it has 22 in the center is because in a tarot card deck, there are 22 major arcana, and then 56 minor arcana. Now, these sort of like major arcana, correspond to like the Fool and the Hanged Man and things like this. Whereas in the minor arcana, you'll have something like the 5 of Pentacles, or the 3 of Swords, or the 4 of Cups. So it consists of the sum of these two, which if I do my math correctly means that there are 78 cards in a tarot deck. I don't know how many of you have ever had your fortune read using a tarot deck, but one of the basic ways you can do it is you shuffle, and then you're dealt 3 cards, and the order of these cards really matters. Unlike in poker, where you can just get a 5-card hand and you can reshuffle them in your hand and it means the same thing for the game. In tarot, it's very different. So in fact, this is your past, this is your present, and this is your future. And so if you were to, swap these two cards in their position, then you'd be exchanging what the card was saying about your past versus your present, which is not something you want to do. So then you can ask yourself, well, how many ways are there of reading someone's fortune? Well, we have an experiment which separates naturally into sort of 3 steps. And this corresponds to 78 possible cards for your first card, your past, and then 77 for your present, and then 76 for your future. And so that equals the number of fortunes. So all of this also goes underneath another sort of mental model for doing combinatorics of probability. And that's something that looks like this. So these are all examples of, this is an example of sampling without replacement and also in the setting where, say, order matters. All right, so let's go ahead and just write down the general formula, and this will connect with something we did on the first day. So the general idea here is that you want to imagine that you've got a collection of objects and they're sitting inside of an urn. And you've got all these different objects, which different colors, and so on and so forth. And you imagine you're going to reach in with your little paw, and you're going to try to grab, you're going to sample from the urn. Now, if you've got a collection of n objects in that urn, so let's assume you have from n objects, and for the you're going to do this k times, then the set of possible ordered draws is, so the number of possible outcomes. Again, this is our size of our sample space, omega. That's going to be n times n minus 1 times all the way down through n minus k plus 1. So this is one of those awkward things where for the first time, which corresponds to k equals 1, you don't subtract anything because there's n possibilities. And so we have to kind of add back 1 to reflect that fact. So there's a slick way of writing this, which looks something like this. So remember, this is a n factorial over n minus k factorial. Same thing as n times n minus 1 times dot 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 n minus k plus 1. And then imagine I have my n minus k down here, and it keeps going. But then on the bottom here, I've got n minus k times n minus k minus 1, so on and so forth down to 1. And you can just see that all these things cancel. And so you're left exactly with that expression up there. So this is a really useful formula. This is sometimes called, this is also written as n reduced by k, or sometimes you'll see p in k. But I usually like to just write it out long ways because I hate remembering things, but I can remember factorial. All right, so let's consider one more example. And this is a famous example in the land of a probability. This is something called the birthday paradox. Here we go. This is the birthday paradox. And the question is essentially this. Suppose there are n people in the room. You want to ask, what's the probability? The question is, probability of two people sharing the same birthday. Well, you know, the surprising thing about this is, even in the case of, let's say, n equals 40. So if you do like, which is about the number of people in this class, the probability that that basically 40 people have all disjoint birthdays, it's actually very low. And so consequently, the probability that two people in our class have exactly the same birthday being high is actually 89% roughly. So an 89% chance. And it's important to say at least two people have the same birthday. And let's sort of go quickly through why this is. And again, this illustrates an important lesson that we considered with De Morgan's law, which is reasoning by complements. So namely, instead of considering this event A, and that's what I'm going to call this guy right here. So here's the event that at least two people have the same birthday. I'm going to call that event A. So here I'm going to invoke something called the rule of complements. Which says that probability of A is the same thing as 1 minus the probability of A complement. So this being the situation where A does not occur. So what this teaches us is that one way of approaching this problem is, instead of counting the number of ways that two people can share, or at least two people can share the same birthday, it's easier to consider the opposite problem. So how many ways is it possible to have no one with the same birthday? And so one way of handling this is we consider how many ways, if I just query people one at a time, can you have disjoint birthdays? Well, it's going to look something like this. So imagine I ask the first person, well, they can have any birthday. So the probability of A complement in our problem is going to look something like, well, imagine I've got 365 out of 365 possible birthdays for the first person. But then in order for the next person to not have the same birthday as the first person, I need to rule out that first birthday that the other person had. And then if I go to my third person, they have only 363 possibilities for a birthday. 363 divided by 365. And this goes down all the way until we get to 365 minus 39, because 39 is 40 minus 1 divided by 365. Which, if we rewrite this in a somewhat fancier way, here we can always draw birthdays, but here we can sort of replace the birthday, because it's it's completely fine for everyone to have the same birthday, even though it's a low probability event. So if I factor out this 365, we know that this question querying what was the birthday is 365 raised to the 40th. That's what happens when I collect all these denominators, across all 40 people. I get that. And so now I need to figure out, well, how do I write this top? Well, this is exactly the thing which I said was 365 factorial, but then divided by 325 factorial. So this is a big complicated number. It's not something you can really put in your calculator. But it turns out that if you do this, you get something like 0.11, which we think of as an 11% chance of no two people sharing the same birthday. All right, so I think that's probably enough for today, and we'll be able to work on the worksheet and try to implement and do some more of these counting problems in class. All right, I look forward to seeing you all in class.